non-invertible symmetries and 2D nonlinear sigma files.
Thank you, Chris. Thanks very much. Okay, morning, everyone. Thank you for coming. So let me start, of course, by thanking the organizers, both for letting me speak to you today and also for the great program of events that they're putting on. So yeah, I'll discuss some work that's appeared in a set of papers that have come out over the past 6 months with fantastic collaborators, Chris, who's here, and also Guillermo Arias Tamargo. So all of us are at Imperial. So being a Blackboard talk, I'll probably be a bit light on references, but you should ask if you want them. And of course, interrupt me whenever you want with questions or comments. So I will talk about a set of interesting generalized symmetries which we've come to understand in these models. And my main aim for the day will be to try and show you how there's a nice set of long-standing pieces of knowledge about dualities that I guess were originally understood in the string theory context that can be applied to this more modern way of thinking about symmetries. And also I'll try and tie in ideas about the topology and geometry of these models and show you how the topological structure of the target space of these sigma models encodes the symmetry structures that arise. So what we've learned in the past decade or so is that a fruitful way to think about symmetries is instead of thinking about the transformations of fields that we would traditionally consider, to think about topological operators. So with an aim to being pedagogical, I'll briefly make some remarks about generalized symmetries. So of course, this is a much broader concept than the traditional notion of a global symmetry, including so-called higher form symmetries, where there are extended operators charged under the action of these symmetries, but also to so-called non-invertible symmetries or categorical symmetries, which I will discuss at length today. And it's proven to be a very fruitful enterprise. There are several new results, good progress, for example, on classifying infrared phases of matter and the properties of different quantum field theories at long distances, and also in constraining, relatedly, constraining renormalization group flows. So of course, two big important topics in quantum field theory. So for example, we heard yesterday in Igor Klebanov's talk about a set of non-invertible symmetries which are important in describing the low energy physics of a joint QCD in 2 dimensions, just as an example. So, like I say, let me start from the beginning. So the normal notion of composition of symmetries is encoded in these topological operators by their fusion. The simplest case being when the symmetry is described by some group, G, in which case each topological operator comes with a label, which is a group element, and if I bring 2 of them together and fuse them on top of each other, then in any correlation function, it's equivalent to the insertion of a single defect, which is simply the one corresponding to the group product of those 2 elements. But in general, you need not have only one element on the right-hand side of these equations, and so you could have operators labeled by some A and B, and find a set of objects C on the right-hand side. And if there are multiple terms in this sum, then you would call this a non-invertible. So we have, I think by now it's fair to say, a decent grip on the structure of these objects, especially in 2 dimensions. But it's not clear, or at least it's not clear to me, that there's a systematic way to go about finding all of them in a given quantum field theory, to just write down and be sure that you've learned about all the topological operators that a theory admits. But we do have several good constructions of them, and so I'll talk about one of those today, which are the so-called self-duality symmetries. So by way of a plan for the next hour and a bit, I'll start by discussing this construction at length, in particular in the example of the compact boson, so that we have a level playing field to start with. And then I will discuss nonlinear sigma models in 2 dimensions with Wess-Zumino terms and their symmetries, their normal group-like symmetries. So there are several good reasons to be interested in sigma models. Of course, they are ubiquitous in string theory. They occur as the effective description of spontaneously broken phases. They can encode strongly coupled dynamics, and so in some sense they could be a toy model for the infrared behavior of Yang-Mills theory in 4 dimensions. So they're good theories to know about. So I'll discuss their regular group-like symmetries and how they relate, like I say, to the topology and geometry of the models. And then using those group-like symmetries, I'll discuss how you can construct self-duality symmetries in these nonlinear sigma models. Then I'll go on to discuss a few applications. In particular, to constraining renormalization group flows, and time permitting, to discuss Ward identities for these symmetries in the context of string theory in particular. So that is the schematic for the next little while. Are there any general questions before I start talking about physics? Good. Okay. Is this too dark to see? That's okay, good. Okay, so let me start by discussing these self-duality symmetries. So the setup is the following. You have a quantum field theory. Let me draw a little diagram. Quantum field theory T on some space, which for us will be 2-dimensional space. And it admits, we suppose, the action of a finite abelian group G. Okay? And so supposing that this G is not 't Hooft anomalous, it can be gauged. And in particular, I can split my space in 2 along some codimension 1 submanifold, which I'll call gamma throughout. And given that G has no 't Hooft anomaly, I can gauge it and generate some other theory. Okay. And when I do this, I get a choice of boundary conditions on this interface gamma, and they can be chosen such that this thing is topological interface between the left and right sides. But for generic theories, groups, this new theory on the right-hand side is not the same as the one on the left. But if you're in some special situation where the theory has a duality, sometimes you can cook up a situation where this gauged theory is exactly isomorphic to the one you started with on the left. Okay? In that situation, you have T on the left, T on the right, and this topological interface gamma between, which you could then see as a topological defect or topological operator, I'll use the terms interchangeably, existing in one single theory. And you could ask whether it's an interesting one. And maybe naively you think it's boring because there's the same theory on the left and the right, but that's not true. In fact, this defect, which I'm going to call curly n, if that's at all legible, always has interesting fusion. So if I take 2 copies of n and I fuse it with itself, or rather fuse it with its CPT conjugate, then I always find that the result is not the identity, but it's a sum of terms. UG here is the generator of the original symmetry group G, which was acting on my theory. Okay? So you always find a sum of terms if G is non-trivial. So you always find that this curly n is a non-invertible defect. Okay, and it obeys the so-called Tamburi-Yamagami fusion rules for the group G. G is abelian and finite for me. Yeah, it will always be some cyclic group or maybe a product thereof. Yes, absolutely. So this is obviously this is a very specific construction that will not happen in every theory. But if you can do this, then this is the definition of a duality defect. This fusion. Yeah, so there's also the interesting property that if you have a theory which admits a defect n with this set of fusion rules, so that there's another set of fusion rules that, then you can show that the theory is self-dual under gauging G. So it works both ways. So yeah, from the self-duality you know about the defect, and from the defect you know about the self-duality. Sorry. That's true. That's true. Yeah, okay. Yeah, so a very special case, obviously, where the thing you need to gauge is some abelian group. But yeah. Okay, good. So so these have been particularly well studied. They were first talked about, I think, maybe 4 years ago, something like that. And they've been studied in 2 dimensions. For example, in the compact boson, where in fact they've been known about for ages, just under different names. And also in the critical Ising model, where they sometimes go under the name of Kramers-Vannier defects. So these are sometimes called Kramers-Vannier symmetries. Also in 4 dimensions related to S-duality, for example in n equals 4 super Yang-Mills, also in class S constructions, and they've been studied from the perspective of the symmetry TFT and from holography. So there's a growing body of literature about these defects. In fact, I think there were 2 papers discussing them this morning on the archive. So let's to have something to pin ourselves on. Let's discuss an example, which is a single compact boson in 2 dimensions, the action for which, just to establish some conventions, I'll write like this, where phi is 2 pi periodic. Okay, so this theory obviously has a U1 shift symmetry, which just shifts phi by a constant, and because phi is periodic, this is U1 star. And this symmetry does not have a 't Hooft anomaly on its own, and so you can gauge it, or you can gauge subgroups of it. So given that I wanted G to be finite, I will choose a subgroup of it. And it's not hard to show, and we'll do so in a second, that if you gauge a ZP subgroup of this U1 symmetry, then it has the impact of sending the theory defined at radius r to the theory defined at radius r on P. Okay, so if that's not clear, I'll explicitly show it in a second. Okay, good. So that's the stage 1 in this construction. I want to ask whether I can gauge this symmetry G and end up back with the same theory I started with. That's not obvious immediately because there are no values of r aside from 0 for which r and r over p are the same. But of course, the compact boson has a very, very interesting property of T-duality, which tells you that the theory defined at radius r is exactly the same as the theory defined at radius 1 over 2 pi r in these conventions. So these, admittedly, for this example, they're not the slickest conventions, but for the setup of the sigma models, it'll be more convenient. Okay, so now I play this game again. I start with my theory at radius r, and it has this ZP shift symmetry acting on it. I gauge it, and that lands me at the theory at radius r on P. I know that is exactly the same as the theory at radius P over 2 pi r. So in particular, if I look at radii at the radius r squared equals P on 2 pi, then the theory on the left and the theory on the right are exactly the same. Okay, so then my half space gauging construction goes through, and indeed I can construct this this self-duality defect. Okay, is that clear? Good. Let me Very good. So instead of, so I think these sort of manipulations on the theory of a given radius are quite clear, but there's a nice path integral manipulation, or even just in the classical action, that will perform both of these operations for you at the same time. It will gauge ZP subgroup of this U1 and perform T-duality. So I want to show you how to do that because that's the technique I'll use later when we talk about the sigma models. Okay. So all you need to do is you start with your compact boson, and I want to gauge the shift symmetry. So I introduce a gauge field that I'm calling C, like this. And so if C then transforms in this way, then clearly this is gauge invariant under this, this U1. But I want to only gauge a ZP subgroup rather than the whole U1. So I introduce a Lagrange multiplier, which I'm going to call phi tilde, which is also 2 pi periodic. Okay. So why does this mean I'm gauging a ZP subgroup? Well, if I integrate out phi tilde, then the untwisted, the non-winding sector of this compact boson just tells me that C needs to be flat. That's its equation of motion. Okay. But then when you sum over all the winding sectors of this compact boson, it sets that the path integral reduces to a sum over these winding sectors, and it becomes a sort of Dirac comb that just sets the holonomies of C to be ZP valued. Okay? So integrating out phi tilde here just has the effect of setting Z to be a ZP gauge field. Okay? So then what I'm meant to do to gauge this symmetry is integrate out C, do the path integral over C, and what you get when you do that is this action. Okay? This is literally just a Gaussian integral for C, so this is exact. And so you see, you immediately land on the radius P over 2 pi r, which was the one we got from doing both the ZP gauging and T-duality. Okay? So if you do operations like this in the path integral, it's a bit slicker. Okay. So the other thing that I will come back to later is to note that if I do this and set P equals 1, then this is just the operation of T-duality, sending R to 1 over 2 pi r. Okay. So the aim will be to generalize this setup to a much broader set of nonlinear sigma models. The compact boson being a nonlinear sigma model is a good place to start. And so what are the ingredients that we're looking to generalize here? Well, we had a shift symmetry. And so I want some analog of a shift symmetry. And we had T-duality. So I'll want to understand how T-duality works for more general sigma models. So the shift symmetry, its analog for more general target spaces of these sigma models will be that the target space has an isometry. Indeed, of course, for the compact boson, the shift around the circle is just a shift along the isometry of the circle, however trivial that may be. So in particular, we're going to study sigma models whose target space has an isometry. I want compact without fixed points, but that'll become clear why. Good. So that's all I was going to say about the setup of the self-duality symmetries and how you construct them. So if there are questions about that sort of background, then now's a good time. Very good. So let me talk about sigma models. So these are theories of maps that I will call phi from a world sheet W, which I'll take to be closed, to some target M. Okay. And the action can be written in the following form. Okay, so what are the ingredients that I have here? I have a Riemannian metric on the target space M. I have a closed 3-form H, okay, on the target space M. I'm assuming that the world sheet, which is, as I say, closed two-dimensional manifold W, can be written as the boundary of some three-manifold V. Okay, so I'm writing the second term, this Wess-Zumino term on V. And the xi are coordinates on M. Okay. And that, yeah, so I mean, these are pullbacks of the derivatives of those coordinates, but pullbacks are implicit. Okay, good. So I wanted to find a two-dimensional theory, and I've written this in terms of a three-dimensional manifold. So it's not clear that this is a two-dimensional thing at all. So what I should do is ensure that the quantum theory that is defined by the path integral with this action is independent of my choice of V. And that is true, provided that 1 over 2 pi h integrated on any closed three-manifold is an integer. Okay, any closed three-manifold in the target M. Okay, so there's some quantization condition on H, or H represents an integral cohomology class. Good. So, like I said, I want to consider the case where there is an isometry of the target. So there's some killing vector K, such that it preserves the metric. And if you ignore the Wess-Zumino term for now, then with this condition, you'll find that shifting the coordinates along the killing direction is a global symmetry of this term, ignoring this. And then you might ask, okay, well, if I want this to be a global symmetry of the whole thing, including the Wess-Zumino term, the B-field term, then what else should I impose? And the obvious thing to impose is that the isometry, the killing vector preserves H. Okay? And that's almost enough. So if you impose these conditions and study the variation of the action under this shift, you find, let me get the prefactors right, that it varies by alpha on W times the pullback. So you have to contract the killing vector with H, gives a two-form. I pull that two-form back and integrate it over the world sheet. Okay? That's, you do a bit of fiddling, plug this in, you have to worry about how the core.
You're going to write this out, say, for this target space, a two-sphere or something simple like that. Is this non-trivial? Is there a non-trivial example to say if it's
Where this is non-zero?
Yeah.
Yeah. Yeah, sure. So if you have a target, say the target is S2 cross S1, and I look at the isometry around the S1, and I put H on this, which is the volume form on this whole space, contracting it along the killing vector just gives me the volume form on S2, which integrates to something non-zero.
So that's something as simple as, say, two-sphere or some any symmetric space.
So it depends on several things. Firstly, which isometry you consider and which B field on that target space you consider. Right. But obviously, if you choose a target space which has no cohomology in degree 2, then this thing is always exact. So this is always that's sufficient. That's sufficient. But you might have chosen, you might have a space which does have two cycles in it, but you've chosen an H such that when I contract it along the killing vector, it doesn't, the projection onto the killing direction doesn't land on a two cycle. So it might be that you have a space, for example, if you put it on a, yeah, so if I have, let me think of an example. So sorry, you want an example of one where this is trivial even though there's non-trivial?
So what I'm trying to say, so okay, you gave a nice simple example. So that's the part two things. So for example, supermodels in symmetric spaces have only one parameter.
Yeah.
And are there examples of those where this will be non-trivial? I'm ignorant of, I can never remember what they're.
Yeah, so I think you can concoct them. So I see no reason why in general they would have no. So the clear statement is that if this is an exact two form, then this clearly vanishes. So if the cohomology of M in degree 2 is trivial, then this is, sorry, can you see this one? Then this clearly always vanishes. So that's enough. It might be that there are actually non-trivial two forms, closed two forms, but IKH is not one of them. But that depends on your choice of killing vector and your choice of H. Okay. Yeah, I think. Yeah. Okay. Very good. Okay, yeah, so as we were saying, so this is clearly 0 if the contraction of H is exact. Okay. And if it's not exact, then, so in that case, the action does not vary under any transformation of this kind. So this is a global symmetry for any parameter alpha. Okay. But because I want this isometry, sorry, I want this isometry to be compact, then this is actually a U1 symmetry. So there's a U1 global symmetry, which is just shifting around the isometry direction. Okay. If it's not exact, then generically this is not 0, but again, depending on your choice of killing vector and H. And generically, this U1 is broken to some discrete subgroup, Z kappa, I'm going to call. Okay. And okay, the details of exactly what kappa is for us won't be particularly important, but just by considering, well, you'll see if I write down the expression. So the value of kappa is this. Why is that the case? Well, if I choose some map from the world sheet into the target space and look at what this quantity is, so I can write this quantity equally as the integral of, so if I alpha is a constant in all of this, so alpha can come out front, and I can write this instead like this. Okay. So this is the W is a closed two-manifold. Because I define it that way. And so this is a 2-cycle in the target. Okay. And so on that 2-cycle, I'm integrating this form, and it follows from the quantization of H that this thing is always in 2 pi alpha times an integer. Okay. And that will be some particular integer. Okay. And whatever integer that is, I can't shift by arbitrary alphas and get this to be a symmetry. But if I shift by an alpha that is 2 pi, that is quantized such that this thing is 2 pi times an integer. Sorry, this should have been, yeah, that's always alpha times an integer. So if I shift by alpha being 2 pi over that integer, then the variation of the action is 2 pi times an integer, and so the path integral is invariant. Absolutely. Exactly. Very good. But that's only the case for this particular map. And because in my theory I have to sum over all choices of maps from the world sheet into the target, I'm summing essentially over all choices of 2 cycles in the target for this thing. Okay. And so, like I say, each one gives some condition on how alpha needs to be quantized. And if you sum over all of them, then it breaks to the greatest common divisor of those numbers. So these sigmas are just a basis of the 2 cycles in the target. Is that clear? No, and they're not. I'll discuss it shortly. Okay, very good. So the generic setting is a bit more complicated than the compact boson, and you don't have a U1. Instead, the Wess-Zumino term, if it has non-trivial level, generically breaks it to some discrete factor. Okay. Please. Yes. Yes. Yeah. So what we'll come to see is that for the gauging of these symmetries, the global structure of these symmetries is important. And so writing things in terms of something that's manifestly globally defined, like H, makes that structure clearer. Of course, H is dB, and I can write it on the world sheet explicitly. You should be able to phrase it in that language, but it's not clear exactly what is a globally defined. For example, in the case of when you have this U1, there's an Noether current associated to it, and that Noether current involves an object which, if you write things in terms of B, it's not obvious that it's globally defined. So you have a conserved current, but it's not obvious that it's actually a one form. So it's a bit difficult to tell what you should class as a symmetry and what you shouldn't, whereas if you write it in terms of H, it's clearer. But yeah, it should be phrasable in that language. Okay, very good. So I want to talk briefly about the geometric perspective. Geometric point of view, maybe, on these global symmetries. So this is before we get to the non-invertibles and the half-space gauging, just focusing on these symmetries. So the fact that there is an isometry, so this killing vector K, which I'm going to say doesn't have fixed points, and is compact, means that the target M can always be written as a circle bundle over some base N. Okay. And now the curvature for this bundle, so it's a U1 bundle, it has a curvature 2 form, and so I'm going to let psi be the dual 1 form to K, such that if I contract K along psi, I get 1. Okay. And then the curvature 2 form of this bundle is just d psi. Okay. So that's one bundle in the game. There's another bundle. Please. No, this statement wouldn't be strictly true without fixed points. Until now, I haven't used it. That's right. I could relax it, and what we'll find is that, so for the discussion of the group-like symmetries, it doesn't matter. For the self-duality symmetries, the condition of self-duality will impose that it doesn't have fixed points. So I'm imposing it from the start to elaborate on some structure, but we would end up there anyway. Good, so that's one bundle. There's another bundle. So I'm going to define a 2-form F tilde by the contraction of the killing vector with the 3-form H, the flux. Okay, and the quantization of H and the fact that this isometry is periodic will tell me that F tilde is also quantized in the right way to be the curvature for a U1 bundle. So this I can see is the curvature of another bundle, which is a circle bundle over M. Okay, so I'll make that more explicit, because this is not the standard way that you would think about a bundle. If we're in the case where I have a U1 symmetry, okay, then IKH, so the contraction of the killing vector along H, is exact. So I can write F tilde is dV for some globally defined 1-form V. Okay. And that's the same as saying that this bundle is trivial. Trivial bundle, okay? So this bundle being trivial tells me there's a U1 symmetry, okay? If instead I'm in the case where it's not exact, I don't get a U1 symmetry, but nevertheless, whether it's exact or not, this is always closed. That follows from the Lie derivative of H along K vanishing, okay? So I can always write F tilde as dV locally, okay? It's closed, so it's locally exact. And V can then always be viewed as a connection, okay? But in general, this is a connection on M, okay? And so this V is the connection on this bundle, okay? So this is telling you about, so it's a bundle over the target space M, telling you about a bigger space M hat, which is 1 dimension higher, okay? So the full structure that's going on is there are 2 circle bundles, and so one of them is over some base N, and it tells me what the target space M is. The other is a bundle over M, encoding some bigger space M hat. Okay? And it turns out that the fibers of these 2 bundles don't talk to each other. So really, I can think of this space M hat as being a torus bundle over the base N. Okay? So this is a circle bundle over M. M is a circle bundle. So it's a circle bundle over a circle bundle. Generically, that wouldn't necessarily be a torus bundle, but it turns out that the two sets of circle fibers don't talk to each other, and so it is. Okay? So I have two circle bundles over some base N, and they're encoded in curvatures F and F tilde. Is that clear? Okay? And whether these bundles are trivial or not tells me what the global symmetry structure of the nonlinear sigma model is. Very good. So, Christian already asked, given that we want to do this half space gauging construction, I want to gauge some symmetries, and so I should ask whether they have Tuft anomalies. So I'm not going to go into the details of deriving the following result, but you go about it the standard way. You study the variation of the action under this transformation, and then you try and couple a background field to cancel the variation, and you see if you can do it or not, or whether there's an obstruction. And so there are two cases. The first case is where we have a U1 symmetry, and we said that in that case, I have F tilde is dV, with V being a globally defined one form. And the anomaly is an integer p, which is the contraction of this one form V along the Gilling vector. Okay, you can. There's a very nice paper of Chris's with Bill Spence from 1980 something, which derives this. Good. So, what are we saying? We have a curvature 2 form F tilde that I get straight from the defining data of the theory, from the Gilling vector and H. Okay? And then if it's exact, I can write it as dV, and I have a U1 symmetry. If the V has a component along the isometry direction, then it has an anomaly. Okay? So this is saying F tilde is exact on M. If it's exact on the base N, then there's no component along the isometry, and there's no anomaly. So this is really telling me that if I want an anomaly-free U1, I need F tilde to not only be exact, but exact on the base, rather than on the total space. Okay, so again, I think this is a nice point where the geometry of the target is really encoding the symmetries for you. Okay, so this is the anomaly. So if P is 0, there's no Tuft anomaly. I can gauge this whole U1. If P is not 0, then I can't do that, but there is a ZP non-anomalous subgroup. Okay. Very good. Now, ironically, the other case where F tilde is not exact, and this bundle is not trivial, where I have a discrete symmetry instead of a U1, is actually simpler, and there's never an anomaly. There's no anomaly. So then I can gauge any ZP subgroup, so that's non-anomalous, for any subgroup, which obviously means that P needs to divide K. Okay, so whether we're in the continuous U1 symmetry case or the discrete case, there's always a non-anomalous ZP subgroup for some P. Okay, in the discrete case, it's any P I like, which divides K. And for the continuous case, it's this P, or subgroups thereof. Okay, so that's a little bit abstract, so I think I will come back to earth with an example. To try and make this a bit concrete. So let me discuss the case when the target is a 3-sphere. So I'm going to write down an action, and we have a metric on the 3-sphere, which Don't spoil the punchline, Igor. Yeah, you will. Yeah. Yes, absolutely. Okay, so this is my theory. I'm putting so there's a metric on the 3 sphere. I've written it in Hopf coordinates. So this is S3 is a S1 bundle over S2. Phi is a 2 pi periodic coordinate along the S1 fiber, on the Hopf fiber. And then I'm adding a B field such that H is proportional to the volume form on S3. Okay, so now let's go through this analysis and see what happens. I want to study a shift of the coordinates along the isometry direction, but given that the isometry is along the fiber, that's just a shift of phi. Okay, and in this case, you can show quite simply that this is exact. Why? Because it's a 2 form and S3 has no cohomology in degree 2, so it's clearly exact. So there's a U1, and there is a, because of the Wess-Zumino term, it turns out that when you write this U1 as dV and ask what the anomaly is up there, you find that the anomaly is K. So I'm going to try and gauge then a ZP subgroup of this U1 where P is a divisor of K. Okay, I know now that's non-anomalous. So if I do that, what do I do? Let me just write this as this is just the base part, the 2 sphere. So how do I gauge this shift symmetry? I introduce a covariant derivative along the isometry direction. d phi, so d phi minus c. Okay, and then exactly like I did before, I'm going to add a Lagrange multiplier term which restricts C to be a ZP gauge field. Okay, and now, so from this point it is 2 or 3 line exercise to integrate out the gauge field. And what you find, so if I do the integral over C, again, it's Gaussian, just do it exactly. You get the answer R squared over, 8. The base part stays the same. And then I get 1 over 8 P over 2 pi R squared integral of 2 pi tilde minus okay, this is what I get. It's a straightforward exercise. So the base part is the same, but then the part that the connection on the Hopf fiber, this term gets a different prefactor. Previously it had R squared over 8. Now we see the T-dual radius going up, and the prefactor in this term gets changed, and the prefactor in the Wess-Zumino term also gets changed. And so what I want to do is demand that this is the same as before. And that is only true if R squared is P on 2 pi and P equals K. Okay? So ultimately R squared is K on 2 pi. And that is exactly the same, as Igor foresaw, as the SU2 level K Wess-Zumino model. Okay? So start with the target space S3 and ask that it admits a self-duality symmetry. You land immediately on SU2 level K Wess-Zumino. Okay. Very good. Okay, so then let me say a few remarks quickly about what the general story is.
This is not one of the usual ones you discuss, which preserve the chiral algebra.
It doesn't preserve the chiral algebra. Yeah, absolutely. Yeah, it's not a Verlinder line. For general, for level 2, it's the same as a Verlinder line. For any higher level, it's not.
I mean, this is But obviously done in a different way, but I'm trying to understand. So if I remember, he just computed the one loop diagram and then argued that it was not a fixed point.
That's right. And then he had an argument from
That very-
holomorphy as well, I think.
Yeah, and so is this then sort of a bulletproof way of avoiding doing that calculation?
So I wouldn't. So yeah. So we'll talk in a bit about how this sort of thing plays with RG and whether you can see that this is conformal from this sort of argument.
Exactly. No, that's
I'll argue that that's true, but maybe in 10 minutes or
because
so.
it's not. I mean, you know the answer, so here you can identify.
Absolutely.
I want to know if Witten had not written this paper.
So I claim that that's true, and I'll probably be in a better position to tell you why in 10 minutes or so.
Okay, good.
Very good. So what's the general story? We know from the start that my model is described by a pair of curvature two forms, f and f tilde, and those are given to me from the data on the target space. They come from the metric and the h. Okay? And gauging this ZP subgroup has the effect of swapping them and rescaling them a bit. Okay? And so there is self-duality, i.e. after they're swapped and rescaled, that the model is the same as when it started, if they satisfy this condition, and if the length squared of the killing vector, which is the analog of the radius of the compact boson, which I'm going to call capital G, is p on 2 pi. Okay, so this is the generic story. So I'm not talking about S3 anymore, I'm talking any target space with a compact isometry with no fixed points. I have this symmetry, I gauge it, and I demand that the result is the same as the one I started with. It must satisfy these conditions. Okay? Very good. Yeah, exactly. So effectively what's happening is that the two fibers of that torus bundle are being swapped, and their radii are being shifted a little bit. Okay, so this comes back to what I was answering to Sakura's question earlier. If you want self-duality, then the radius of the killing vector is fixed to be a constant. So it could never have a fixed point anyway. So if you started with an isometry with a fixed point, you would never have self-duality. And this also highlights, I think, the nice point that you can also never, so if f tilde is 0, which is when you have no Wess-Zumino term, then the only solution here is that everything's 0. Which is telling you that the Wess-Zumino term is crucial for this self-duality. Okay. So in the compact boson, you obviously don't see that because the dimension of the target space is small enough that you can't have a Wess-Zumino term. No. Good. Okay, in view of time, I think I'll leave that. So there are a few obvious generalizations that come for free. So the first is, what if we didn't talk just about one isometry, but about n abelian isometries? Okay, so I have a set of killing vectors labeled by some index little m. And then the same thing happens. For each one of them, I get a pair of U1 bundles with curvature 2 forms. And what happens as I gauge, I have, let me write a U1 to the n symmetry, depending, like we said before, depending on the properties of f and f tilde, this may be U1, it may be some discrete group, but the story is the same as before. So let's, for the sake of argument, let's say it's U1. And I can gauge a ZP to the n subgroup. If it's non-anomalous, the anomaly story goes through exactly the same as before. And the self-duality conditions are very similar. The first one looks exactly like before. So for each isometry, you have this condition on the curvature 2 forms. The second condition about the radius of the killing vector gets generalized slightly, and it becomes a condition that looks like this, where E is a matrix. And I'm not going to go into the nitty-gritty of exactly how you get this. This is to do with the lengths of all the different killing vectors, and this is to do with the projection of the of H onto the different isometry directions. Okay, so this G and B there's a load of definitions that I would have to write down that I want to skip. If someone's interested, I'll happily discuss. No, so you could, very good. So you could gauge ZPI subgroup of each one, provided that each one of those subgroups is non-anomalous, and then these results, so each of these P's, maybe I should have called this M and then it would match the other labels, each of these P's comes with a label as well, and the duality conditions become the M over 2 pi. Yeah. Okay. Yeah. Okay. And the other quick generalization before I talk about RG flow is that in the compact boson, you know that you have another symmetry altogether that I never mentioned. Wait, please. Yes. You could gauge diagonal sub. Yeah, I think off the top of my head, I don't know the conditions that will come out, but yeah, there could be a diagonal subgroup that's not anomalous, and you could gauge that. I'll cover myself in chalk. There we are. Yeah, so you can play around with exactly what subgroups you want to gauge in that case. So in the compact boson, you have winding as well. You have a U1 winding symmetry. What does that become in this more general setup? Well, so we've talked about T-duality. And so what happens is I have one target space, and I'm saying it has an isometry. If I study the T-dual, which we said we get to by doing exactly these operations, but with p equals 1, okay, then I get to a different model on a different target space that will always also have an isometry. Okay? And I can ask whether there is a symmetry that is a shift along that isometry in the T-dual. Okay? And that is exactly what winding is for the compact boson. Okay? So you can go through exactly the same analysis I've just done, but in the T-dual frame, and then extrapolate the results back to the original frame that you wrote down, and you learn about the dual symmetries. So this comes, without going into detail, from the T-dual isometry. Okay. So generically, you have some Z kappa symmetry associated with the isometry in the first frame, and you have some Z kappa tilde maybe symmetry associated with the isometry in the T-dual frame. These have a mixed anomaly in the very analogous way to the momentum unwinding of the compact boson, and there's a nice story about how the self-duality conditions play with gauging these symmetries with the mixed anomaly. Okay, so in this case, if I gauge a ZP cross ZQ subgroup of this, it's a slightly more general thing I could do instead of just gauging part of the symmetry from the isometry. I can gauge a part of the isometry and a part of the winding. I need P and Q to be co-prime in order to avoid an anomaly. But then, if I do that, the self-duality conditions become these. Okay? So things are framed sort of in terms of P over Q. Okay, so I know that last bit was a bit quick. I just wanted to flash a couple of more general things you can do. Are there questions about that? Well, so I'm going to talk about applications now. So if there's questions about the construction, then now's a good time. Let's get rid of this. Okay, sorry. 2. The world sheet is 2-dimensional. The target is whatever. The T-duality. Yeah, you can't do. But if you start with a world sheet that's 3-dimensional, this is so the shift that I'm talking about is a zero-form symmetry. If you gauge a zero-form symmetry in 2D, you get back a zero-form symmetry. If you gauge it in 3D, you get back a one-form symmetry. So you would never be able to get back the same model you started with. That's true. Yeah, that's true. Absolutely. Yeah, absolutely. Yeah, that's on the to-do list, but hasn't been done. Okay. So let me talk about RG, or RG constraints. So, yeah, I mean, it's sort of a difficult subject to talk about because the renormalization of sigma models has been studied to death. So say something new is a hard one. But so one thing that you can generically use in trying to study renormalization groups is global symmetries. In fact, it's probably about the only thing you can use. So having learned about the existence of a new global symmetry, we should try and ask whether it tells us anything. So in particular, if I have some theory with a global symmetry, and it's not conformal, and I let it run, then I should expect that global symmetry remains along the flow, that terms breaking that symmetry won't be generated by the RG. Of course, if I explicitly break it with a deformation, that's not true, but if I just let it run by itself, I should expect that the global symmetries are preserved. So in particular, if I start with a theory, start with a nonlinear sigma model such that Pf equals Qf tilde and G equals P over 2 pi Q, then I know it admits one of these non-invertible self-duality symmetries. Okay? And I should expect that under RG, that symmetry is not broken. Okay? So in particular, you should expect, so these are quantized things, so you wouldn't expect this to be broken anyway. This is not. This is some parameter in the metric. Capital. This is the length of the killing vector. Okay? So this is in general a continuous thing. And what I'm claiming is that if it starts off at this value, then it will remain at that value. Because if it changes, then my non-invertible goes away. Okay? The self-duality goes away. So let's see if that happens. And I will give you some strong evidence that that is true, and then try and learn something. So the first thing to say, importantly, while the example I showed you earlier of Wesson-Witten is conformal, generically you can satisfy these constraints in non-conformal non-linear sigma models. So this is not a vacuous question. Okay, so the one loop beta function for the metric is very well known, and it takes this form, IKL J KL. Okay, one loop with just a Wesson-Witten terms. The original result with the Ricci tensor was known from Friedan's work, I think, and then suitably generalized. Now it's known to two loop. I think there's some results on three loop as well. I'm not sure of the state of the art. But so let's start with this. And I want to understand what the beta function for this capital G is. Okay? And like we said, capital G is, sorry, J, Ki, Kj. Okay. So I'm going to choose coordinates on the target, which I'm going to denote by y, mu, and x, such that x is adapted to the isometry direction. Okay, so the killing vector just lies along x, and x is a periodic coordinate because it's a compact isometry. And then using this, I have that G is just the xx component of the metric. Okay, so I can immediately just write down, I plug in ij equals xx in this choice of coordinates, and all I need to do is find a particular component of the Ricci tensor and a particular component of this. Okay? And there's a nice calculation you can do to do that. You'll find it in the paper that came out this morning. And what you find is that beta G at one loop is given by this expression. Okay, so the term that talks to the metric, the Ricci term, reduces just to the square of the first curvature 2 form, and the term that talks to the Wesson-Witten term just gives you the other curvature 2 form. Okay, so you can immediately see, if I plug in these conditions, this vanishes. Okay, so clearly at one loop, if I started with these couplings, this one doesn't run. Okay. A stronger thing is true, which I think is very cool, that if I want this to vanish, forget that I knew about this constraint, okay? And I just say, consider a target space with an isometry, okay? Then I would arrive at this beta function for the radius of the isometry. Okay. And I'd say, I wonder when it's fixed under Rg. I wonder when it's Rg stable. So let's just demand that beta g is 0. That's clearly satisfied when f tilde is 2 pi gf. Sorry, not so clear. Okay. So demanding beta g, demanding that the radius of the isometry does not run, I get to this condition, but because f and f tilde are curvatures for U1 bundles, they are quantized. Okay. So this can only be the case if 2 pi g is rational, i.e. it can be written as p over q. And so in fact, demanding that this coupling is fixed under Rg is true if and only if there is a non-invertible symmetry. Okay, I think that's quite a nice result. So you can then go a bit further and write down the two-loop beta function, and you'll find again that this vanishes. There's a very neat calculation, but I'm not going to go through it. That this vanishes exactly to two-loop as well. And I think the fact that there's a global symmetry protecting this is good, strong evidence that this should be preserved. This coupling should be exactly preserved under Rg. And in fact, so this is now coming back to your question, that's exactly the case for SU2 Weissminer-Witten. So I started with a theory with only one coupling that can run because of the symmetries of the target space. So if that coupling is protected, then the model's conformal because there's no other couplings that can run. Well, it's scale invariant. That one happens to be unitary 2D QFT with discrete spectrum, so therefore it's conformal too. But okay, it's a slight technicality. But so if I start with sigma model on S3 with R squared equals P on 2 pi, then I know there's a non-invertible. I know that protects R from running. That's the only coupling that could run, therefore it's scale invariant. So I think you know that.
There is a coupling that can run. It's a non-trivial flow.
Yes, but if it starts at the value. Yeah, so in the UV, study the one with that coupling, then I know there's another symmetry, and then I know it can't run.
So you fix, if you wish, in the flow language, then you fix the value at which the fixed point, at least at one loop, you know exactly where the...
Yes, this isn't, so obviously at any other value of R, it's not protected at all. There was no symmetry to start with.
Is it still resolved? I mean, do you have to use the beta function to see this, or?
So I think that well, I think that depends on your point of view. I think if you subscribe to the point of view that global symmetries are not broken by Rg, then this is a global symmetry, therefore it's not broken.
It's a global symmetry, ergo nothing.
Absolutely. Or if you need some convincing that that's true, you start studying beta functions and you find that they all vanish.
Just mentions that checks up. It's a check.
Yeah, exactly. Yeah, so I think you could derive that S3 with that value of the radius was always conformal from the existence of a non-invertible. For Weissminer-Witten, I thought it was exactly conformal.
But this R squared direction to beta function is going to normalize the relation between the radius and k, right? There is there is a shift k to k plus 2.
Okay, this I'm not aware of the story. So yeah, I'd love to talk about this.
But I think you found something that's not renormalized, but the solution to beta gravitational beta function to 0 does undergo correction.
That's true, and okay. So now I'm treading into territory that I'm not so familiar. But so the Weyl anomaly coefficients are not the same as these beta functions for general sigma models. There's an extra there's the Weyl anomaly coefficients are these beta functions plus an extra thing, and I can't remember the form of that extra thing. But
that's a separate thing from the beta GIJ has the
yes.
Riemann squared and
Yeah, so that term also vanishes. So you can check to two loops as well that this beta function vanishes. So if you have these conditions, you can write down, you have to choose a scheme. Okay, so there is a scheme where the one loop one vanishes, the two loop one vanishes, And because there's a global symmetry, I think it's strong evidence that it vanishes. If you choose a different scheme, that's not true, and then you have to start worrying about. But that's a standard story with this type of thing, I think.
I thought that there is this 1 over k expansion.
Yes. Yes. But you're saying this is a one-loop result. Yes.
And definitely it's not renormalized by
Yes.
but the usual radius of 3-sphere k relation is not protected.
Right. I would be very interested to talk about that and learn more about it. I'm not aware of that story.
Maybe just DS2 and then DS1 is fixed because it's simply but he has around 3.
Yeah, this is round to start with. Yeah. No. This started as round S3. The roundness, but that was preserved anyway without the non-invertible. Exactly. It's not going to get stretched. Exactly. Yeah, so the question is whether the radius gets renormalized, and my claim was that if it's at this value, then no. And that value is what coincides with Westermino width. Yes, sorry, I'm lazily switching letters.
I mean, it's been a long time since I worked on this, but I thought that the shift of k by 2 second one possible.
Okay,
Ah, yeah, that's that. This is just bosonic.
Just bosonic, yeah. Yes, indeed he has. They're wonderful papers that are spectacularly dense.
What's non-trivial is the dilaton beta function.
Yeah, the radius of the 3 sphere.
But,
So you're saying that if you write down the known like r squared and each term by itself.
Yeah.
Yes.
So because they can be written in terms of exponential torsion, and because on group manifold curvature the metric and the beating beta functions vanish identically, but the dilaton one doesn't. And it's because the dilaton one doesn't vanish, that leads to a shift in the central charge. So it's a non-trivial central charge which comes from that. But the metric beta function, and hence the story about the radius, there isn't a change.
Very good. So let me. Okay, how are we doing for time? Okay, so as maybe I skip a. Sorry. Okay, very good. So let's say one more thing about RG, and then quickly talk about ward identities. Okay, so an interesting variation of the example is to start with a squashed S3, which lines up more with what Christian was saying. So you start with a metric. Let me write r squared on 4, and then I have a 2-sphere base, and now I'm going to put some squashing parameter like this, and the same h as before. Okay, so I start with this model. This still has a U1 isometry around the fiber direction. It's now just slightly squashed. And so if you calculate G, you'll find that it's r squared L squared. And now exactly the same story applies. So if I start with this being some value k over 2 pi, then everything I've said before goes through. You find that this is self-dual under gauging a ZK subgroup of the U1 symmetry, and there's a self-duality defect. And in fact, the RG flow of this model has been studied a few times. More recently in a paper from 2021 by Schiffman and Scherbrink. So it flows in the IR to SU2 level k to the fixed point. And they noted in this paper that in fact this combination, they were doing a two-loop analysis and noted as a curiosity that this seems to be fixed under RG, and they gave some conjectural argument that it should be preserved to all orders just based on the form of the RG equations that were coming up in that particular example. So now there's a global symmetry protecting that, which I think is quite gratifying. Okay, good. So, please.
But if I remember correctly, in the sequel one example for my analysis, data groups in the right way, there are some landmark information which are out the scalar. Precisely, it's some weird operator to make out of momentum.
There are certainly, yeah, so sometimes there are operators which commute within non-invertible, and you could have some symmetric flow to some other phase.
Then how could you, because this is the pure flow, the one with just sigma.
Exactly, exactly.
More examples, or you're going to move on? Because I have a question about examples.
Please ask.
Okay. So, there's a very old story about sigma models, which with theta terms flow to CFT.
Yeah. Absolutely, yeah.
And so, for example, there were thought about wrong statements that if CPN theta equals pi would flow to SUN level 1. That's wrong.
Mhm.
And the way it was realized it was wrong was that you look at the discrete symmetries of the infrared fixed point, if you wish, and you see that there's not enough symmetries in your original theory
Right.
to protect this. So the question is, you're identifying what in at least some cases are previously unknown symmetries.
Mm.
So do you have any examples where you can now establish this flow does happen?
Yeah, that's a very good question.
The naive symmetries wouldn't allow it.
That's a very good question. I would really love to have a good example of that,
So
but
you don't get-
no.
there must be some where-
Yeah, so right, yeah. So the obvious one that you would really like to study is the sort of like Haldane conjecture type, where depending on the level, you get gapless or gap phases. Yeah, but if I remember correctly, now I'm off the top of my head, I don't think there's an isometry that you can use that works in that case.
No,
The-
that's probably not. I mean, there's like this flag manifold. In fact, people revisit it. I think there's Affleck wrote a paper. I mean, much more. He wrote these papers 40 years ago, but then there was one maybe 3-4 years ago on these flag manifolds. I seem to remember cyber. I mean, so people,
I see.
those who were there at the time, revisited this question.
Okay, very good, very good. Sounds like I have some reading to do. Yeah, no, that would be great. A real kicker of an example would be fantastic. So yeah, I'd love to, if you have some references there, that would be great. Okay. Okay, so for the last 10 minutes or so, let me quickly talk about Ward identities for these non-invertibles. So, I mean, of course, the normal story is you want to try and impose, see the consequences of some global symmetry on correlation functions in your theory. And we'll see that the generic situation for non-invertibles is that you don't really end up constraining a single correlator, you end up relating different correlators in some sense. So let's see how that goes. So I want to start, let's say let's say my world sheet is a torus, and I put some operator, let me get a color. Better. Okay, and I want to ask how does this operator transform if I act on it with this non-invertible symmetry? And we know in the generalized symmetries language, we do that by wrapping it, and then I can shrink this defect, and that will give me the transformed operator. And now how do I go about finding these Ward identities? Well, I start deforming n. It's topological after all, so I can move it how I want. So the operator stays still. So let's start by taking the top bit and wrapping it, moving it around the vertical cycle. And I'll end up with a situation like this. I hope that's clear. Okay, and now what do? Well, I know about the fusion of this line. More properly, I want to use an F move, but okay, that's terminology. Let's not get into it exactly, but okay, so I can use, more colors, here we go. I can use an F move, and essentially because the fusion of n with itself gives a sum over the group generators, this yellow line is denoting a sum over the group generators. Okay, and there's a factor. The F symbols come with it. Okay, and now I can move this. I'm not drawing all the slashes. This is a torus, but I can move this line around the horizontal cycle and get to, good God, set up like this. Okay, very good. So I've just taken this left one and wrapped it around the horizontal cycle. And finally, I have these two non-invertible lines. I can fuse them together. And all I end up with, in the right color, is this configuration. Okay. So what is this telling me about? This is relating the transformed operator, we said that's what this was, to the untransformed operator, but in the presence of a mesh of topological lines. Okay, so if this were an invertible thing, I wouldn't have the topological lines, and this would just be relating the transformed thing to the untransformed thing, and that's the normal form of a Watt identity. So this isn't quite, like I said, this isn't quite relating, giving a relation on a single correlator. It's relating a correlator without lines to a correlator with lines. But absolutely, this is generic for non-invertible. Absolutely. No, absolutely. It's a question. It's semantics. It's semantics. For invertibles, you wouldn't get this, and I think that's what most people are used to. So I'm just saying that's different. Okay, good. So then you can try and explicitly write these down in examples and try and see what constraints this gives on correlators. And there's an example that was studied. Let me get the reference right. This year by Bharadwaj, Nero, and Rompelakis, of the bosonic string with one compact direction in the target. So there's essentially one compact boson going around, and then you can do this sort of thing. And they explicitly verified that this is indeed satisfied by one of the vertex operators, and did a very nice calculation to show it. So now that we know about the same set of non-invertibles in a horde of other sigma models, we have some work in progress to try and generalize this and write down Ward identities for those as well. One thing to note is the type of relation that you get here clearly depends on the genus of the world sheet. So you end up with a set of lines inserted on each non-trivial cycle. And so in string theory, you have the genus expansion, and essentially the selection rules that you get from these Ward identities at each order are different. So the symmetry is broken by the expansion. Okay, very good. So let me wrap up. So yeah, so hopefully I've convinced you of some interesting new results concerning dualities and symmetries of non-invertibles, and how they can be used to tell you something non-trivial about the renormalization group flow. So some outlook that we have, we want to understand these Ward identities better for more general classes of sigma models. Hopefully supersymmetric sigma models shouldn't be too distant. That there's old work discussing the gauging of isometries in supersymmetric sigma models, and the constraints on the target space aren't so different. So hopefully something like that's possible. Maybe I'll end on one interesting thing that I noted a couple of weeks ago, which is that there are models, for example, if you study M being an S1 bundle over S2 cross S2, there are models where if you study this target, you put given B field on it, and you demand that there's a non-invertible, you find, again, that the radius of this circle has to satisfy a particular condition. It turns out that when that condition is satisfied, this M is one of the so-called TPQ spaces, and it's precisely classically integrable at exactly that value. Okay, so if you study this not on TPQ, on some generic manifold of this type, it doesn't admit a non-invertible, and it's not integrable classically. But if you study it at the radius where there's a non-invertible, it's also classically integrable. So it seems like there's some, it's clearly not generic, because there are plenty of integrable models which don't have this property, but that sounds like an interesting thing to understand. Okay, so I'll leave it at that. Thank you very much.
And I wonder if there is some deformation of your construction. This is invertible symmetry fluxation.
Yeah, so it's something somewhat analogous to the compact boson. Yeah, I agree. That would be nice to understand. Yeah, absolutely. With, akin to your work with Schotter on that. Yeah, no, I agree. That would be a nice direction to understand. Yes, exactly. But so the thing with JJ, right? Let me remember how this works. So if you start with Weseminer width, so you start at some radius, which is the Weseminer-Witten one, and then if you do JJ bar along the fiber direction, it squashes that direction, and you don't change R, but you essentially introduce the squashing of the three-sphere along that direction. And then because R doesn't change, neither does P. This no longer, for L not equal to 1, this no longer has the non-invertible. So I think it breaks it immediately. Though the formulae are very, very similar, but I think the things that are fixed, so for the non-invertible story, this combination is fixed. For the JJ bar story, R and P are fixed, and you start introducing L. So yes, absolutely, absolutely. But yeah, something like that maybe would. And you have the Konefeld story. Yeah, so being more precise, the example that I know about is when P is 1, then you have the integral for any Q. Then you have the integrability story. So this is written about in a paper of Arcades with Nat Levine from 2021, I think. But then I think this story goes through for any Q with P equals 1.
Usually non-invertible symmetries are not enough to share integrability.
Right. Excellent. I look forward to it. Very, very good. Yeah. So the one thing, I mean, now this is my own curiosities. So I understand that there's this this idea that if the integrability should somehow be sufficient to be stable under RG. You know, you have infinitely many conserved charges, and somehow that should.
If it's integrable, you can then study perturbation.
Sure.
And then there's arguments that let you understand does the perturbation preserve this integrability?
Right.
There's this whole teleological thing. And in some cases, you don't have to do any work to see whether this is true. You can just see by looking at various spaces of operators.
I see.
There must be these charges needed.
I see.
In some cases, they're integrable where that doesn't work.
I see.
So the point being, you can't say it's integral. You can say it doesn't look like it's integral, but without doing a detailed calculation,
You wouldn't see the structure.
But
I see.
So it's a good. So these are good signs, though. These are very useful.
Okay, excellent. I see. Thank you. Not in exhaustive detail, of course. There's a long and beautiful story, I guess. So we've done it over a 4 torus. So there's so because you want to satisfy something like you want to satisfy something like this, and f being the curvature of the S1 bundle. If you just do it on a, if you have a trivial bundle, so I want to study an S1 bundle over, say, T4 or Tn. If it's just a trivial bundle, then f is 0 and you don't get anything interesting. So you have to have some non-trivial circle bundle over this. So you have to study nil manifolds in that case to get anything interesting out, but then you can find particular nil manifolds where that does happen, where you have the non-invertible. But no, any more general bases we haven't studied.
Function has some ambiguity, and you can fix the ambiguity so that the radius is not renormalized.
Yeah, so there's so my understanding is so the two-loop beta function, because you have many couplings, there's scheme dependence, and so you have to choose one. And there were several papers that came out at the same time back in the day. One with Chris and Paul Townsend, another with Arkady and Medsayev, and there was another one that I don't remember. Arkady's one, for example, is very explicit about including choices of scheme. And so the calculation that we've done to show that the two-loop beta function vanishes is in a very particular choice of scheme. If you start changing scheme, then it doesn't look like it vanishes anymore. But if you start changing scheme, there are also alpha prime corrections to T-duality. And so you can try and match those alpha prime corrections to the self-duality relations with the alpha prime corrections that come up in the RG flow.
Because the exact dimension of the WDW model has k plus 2 in the denominator. So you have to get it from somewhere.
Yeah.
You're saying it's not from renormalizing radius, but there must be some.
Yeah. Okay. Yeah. No, I agree. That should be understood. Exactly. Yes. Yes, that's true. Yeah, no, that should be understood. I agree.
I think it's also early, right? Is it 1 p.m. in Otter? Otherwise, let's thank that.
Thanks very much.